Oh, greetings, everybody. Here we are at chapter 3 of our quantum mechanics class. And before we start, let me remind you that their Q&A from last week is in the class folder. And it's a little technical this time because a couple of the questions that were asked, you probably should take a look at the questions just so you need to know what people are thinking about. The answer, as I say, a little more technical than other sessions we've had. So anyway, that's available now. Also, before we start, John Anderson just asked, "Am I going to publish my book?" I'm talking to a publisher now, and we're at the early stages, so I'm not sure if they're going to go ahead, but they have shown interest, and I'm preparing sample chapters for them. So I'll keep you informed about that. If something happens after this class ends, I'll communicate through CSU, and you'll know about the imminent publication if it happens. Things are going to look a little different today. I've switched to presenting with from a PDF rather than Microsoft Word. So you'll see me switching the size and width of the screen to make material available. You'll see the cursor here is gigantic now because I've had some questions or some requests that I make the cursor bigger so that you can see exactly where I'm pointing. And that's why the cursor is so large. All right, let's get started. This is the famous physicist Richard Feynman at the Nobel Award 1965, I think. He and two others won for their advance in the field of quantum electrodynamics. He was a character, is the only way to say it. And here he is with the Princess of Sweden, and she seems to be amused by his dangling cigarette. All right, so let's go now. Now, this is where you're going to see when we get to a topic that I'm going to address in detail, I'll make the page wider so you'll be able to see all the details. You can take a look at this little cartoon at your leisure. Today, we're going to summarize what we've done in the prior 2 weeks. And in discussing the summary, I'm going to weave in this issue of wave functions. That's a central part of what we're describing today, because today's presentation pertains to the modern version of quantum mechanics that emerged roughly 1928 or so, and it's still the standard that is taught to students today. There are more advances that we will talk about later, but what I'm going to show you today is the basis of the quantum mechanics that has provided us with so much technology in the form of electronics, medical instruments, and so forth. So let's go through this list, and here's where I'm going to switch, and we're going to go to this view. So I want to talk about these key points. Now, you have already heard or seen most of the vocabulary that you'll need to digest what I'm going to tell you. There's a few new words and symbols, but not much. Here's the essential thing we're addressing today. If you're dealing with a quantum system, all you need to describe it is a mathematical entity called a wave function. And did somebody have a comment, question? Okay. A wave function is all you need, and I'm going to describe to you how we get a wave function. It's not an arbitrary thing. You don't just make it up. You have to do a little math that takes into account the environment in which the quantum system exists. The simplest quantum system is, say, an electron or a photon. If you know the environment and its properties, and I'll describe this in more detail, then you can create the wave function. And the wave function tells you everything. It tells you how that system is going to evolve in time, which is an important thing. When we do physics, even the physics of Newton and subsequent researchers, mostly we're interested in what is it, tell me what the system is doing now, and then give me the tools to describe what it's going to do in the future. I want to see how a quantum system evolves and use it to make predictions about how nature functions or how experiments are going to unfold and so forth. The interesting thing about quantum systems is that there are two intervals of time that we talk about. The first is when the quantum system is just sitting there and we haven't touched it, we haven't tried to make a measurement. We have a way to use the wave function to calculate how the system is going to evolve. And of course, if we don't do an experiment, we don't know what it's doing. So that first interval is sort of invisible to us. It's the evolution under the influence of the wave function of a quantum system. If we then make a measurement, a new time interval comes in, and I've listed them here, one and two. The second time interval is what happens after you make a measurement. In that interval, the wave function is no longer relevant. It only describes what happens before you touch the system or make a measurement. So we have something here that's very unlike the classical situation described by Isaac Newton and Maxwell when he invented his description of electromagnetism. All prior physics, prior to quantum mechanics, had if you had a way to describe a quantum system, that you only needed one equation, for example. Here we have an equation, and I'll tell you now, it's called the Schrodinger equation. I'll show it to you in a minute. The Schrodinger equation describes the time evolution of a quantum system until you make a measurement or until it interacts with another system, including a macroscopic system, like the walls of a container or something like that. That changes everything. But the Schrodinger equation deals with the time before you make contact with the quantum system. And we know the Schrodinger equation reliably describes the evolution of quantum systems. If it didn't, we wouldn't have electronics. We wouldn't have lasers and all those other things that derive from understanding the quantum world. So I'll show you a drawing of this in a second, this partition in time between prior to an event and after an event. And one of the great mysteries that is still debated, even though quantum mechanics is now 125 years old, the debate continues about what is actually going on in nature that forces us to use a descriptive equation, namely the Schrodinger equation, for part of the time of that system, and then a completely different result after a measurement. We'll get into this. Then we have this very important rule developed by Max Born, in which he described, where's somewhere here should be the first introduction of this symbol, pronounced psi, if you put a little p in front of it, psi. It's a Greek letter. What Max Born showed was that the probability for outcomes of measurements from quantum systems is described by the wave function squared. It's a little more technical than that because the wave function lives in a mathematical world called complex space, but we don't care about that now. This symbol is going to pop up, this square symbol is going to pop up over and over because Max Born found that this gives you the probability of a certain outcome for a quantum system evolving according to the Schrodinger equation. We also know that quantum systems, starting with the same wave function, can end up with different outcomes. When you measure, you actually have a experimental apparatus and make a measurement. You can start with the same conditions, but you get different outcomes. And this psi squared tells you the probability of which of those outcomes you're going to get. We already have talked about the fact that quantum systems can exhibit particle or wave properties depending on the way you interact with the system. The same wave function exists, but when you make a measurement or the design of your experiment or the natural setting in which a quantum process occurs, can exhibit particle or wave behavior depending on the situation that the quantum system is in. We've also talked about the fact that quantum systems can have spin. Almost all quantum particles, photons, neutrons, protons, electrons, and all that, most of them have a spin property. A few have zero spin. They have some special or property that they have zero spin. But when we talk about spin, I'll remind you the spin can only have quantized values, that it could be +2 or -1 or +3 or 0. But in between those values, spin does not exist in those cases. We have the uncertainty principle, we touched on it a bit last time, that says that if you're making measurements, there's an overriding restriction on how refined your measurement can be. Not because you can't build a really clever experiment, but because nature does not like to be confined in certain ways. We'll get into the details of that. One of the most extraordinary features of quantum mechanics is entanglement. That 2 there just refers to a footnote, not a mathematical square symbol. Entanglement involves the behavior of pairs or groups of particles that are prepared in a special way. And once they're prepared that way, as long as you don't interfere, the particles that are in an entangled state can be correlated, even if they're entangled in a process that entangles them, and then they're separated by enormous distances. As long as you don't allow those particles to interact with other quantum systems, the properties of that family of entangled particles is retained forever. This is our first encounter with this concept, except I showed a cartoon in the first lecture, but this is going to be a central topic for the rest of our time together. That entanglement dictates some of the strangest properties of the natural world. Now, there's some more material here to remind you of where we have been. I'm now going to show you the double slit, or let's go back to this, a double slit experiment. Remember, I explained that Thomas Young in the 1800s showed that light projected onto a double slit like this doesn't produce two bright spots that you might have expected from two openings. Rather, you see this interference pattern. And I'm going to show you that if we repeat that experiment, but we don't use light, we use electrons. And if we set up an experiment that forces the electrons through a double slit, an interesting thing happens. So it's gonna take me a second here to set this up because I have to stop sharing. And then I'm going to share again so you can see. Let's do it this way. And I'll make this bigger. So you should see a panel, a rectangular panel with little dots appearing. This is a film loop taken from an actual experiment where electrons were projected at a device that simulates for the electrons a double slit setup. Only one electron is in this experiment at a time. That's why you're seeing individual dots appear on the screen. But notice what's happening here. Each electron encounters a system with two slits, and the electrons pass through those two slits. We don't know which slit they're going through, but they exhibit wave-like properties because notice right here, we're collecting more and more dots in this region, and a pile of dots is appearing here, and another part here, and in between there are fewer dots. This is the same kind of interference pattern that I showed you in the photograph just a moment ago. What we're exhibiting here is an interference process where electrons behave like waves, even though there's only one electron in this experiment at any given time. Quantum mechanics predicts this, and you see we're seeing interference fringes where the white dots are. Now let's go back to our So this static photo shows you what I'm talking about. So what we have is a situation where quantum particles are particularly electrons, which we normally think of as particles. They are experiencing a double slit experiment type setup, and they are producing this kind of pattern, even though only one electron is in the experiment at a time. It's extraordinary, but it's exactly what the Schrodinger equation predicts. This is part of what what I'm going to show you is next is the issue of the question of why there are two time intervals in the life of a quantum system. This is typically called the measurement problem. And there's much debate about what this all means. So let's take a look at a cartoon I created to try to describe this. Here's time evolving, and there's two things here. In green, we have the wave function, abbreviated by the Greek letter psi, and that wave function, when it is squared based on the rule of Max Born, you square it to get the probability. So there's the square of the wave function. And that tells us the range of outcomes of an experiment if we decide to make a measurement right here. The probability of what value we're going to get from the measurement is somewhere confined in this range from, just imagine drawing a vertical line here. If we make the measurement right here, let's say, then we have a different range of probabilities because the wave function is changing over time and the trajectory of the wave function, this green line, is dictated by the Schrodinger equation. That's what tells us how the system is going to evolve. And then we make a measurement and we end up with this value. And the Schrodinger equation and the wave function are no longer relevant. And if we repeat this, if we take the same quantum system and run it again, we have this value, and then we're going to start a new experiment right here, and we have the wave function evolving. And if we make a measurement, we get this value, and so forth. So this is called the measurement problem. What is it that happens right here that changes the system from evolving under the control of the Schrodinger equation to having just a single value? So if we go back up to this drawing here, what we mean by having a transition from the system evolving under the Schrodinger equation means there's no dot on the screen. And if we do that movie I just showed you, a dot will appear, perhaps this one right here. And that's the value that the system took on at that instant. And then another electron comes into the system, and we don't know what it's doing or where it's going to land. We know probabilities. In fact, after doing this experiment over and over, we know it's very probably going to land in this region, this, or this, and very improbable that it'll land between those piles of electrons that came before. This is called the measurement problem, and much debate we will talk about in future lectures. So let's talk about the Schrodinger equation. This is Erwin Schrödinger's product in 1926. Of course, we're not going to do math, but let's take a look at what he built. He used his intuition and the knowledge he had from the way that conventional or classical physics behaves, and put this together and shocked the whole community. And let me tell you what is going on here. We have, let's ignore that I for a second. We have Planck's constant, which we heard about in the last 2 weeks, with a little bar across its vertical part. That means it's Planck's constant divided by 2 pi. Then we have some mathematical symbols, this sort of a reverse 6. That tells the mathematician what to do. And there's time. And here's the wave function. And this is a one-dimensional example. This wave function is different at different places. That's what X refers to. And it's different at different times. So the wave function, which I haven't yet told you how we get that, but it changes with position and time. Again, we have Planck's constant. We have the mass of whatever object we're talking about, an electron, the different version, of course, if you have a photon. Here's a mathematical business that you do. And this V is a description of the energetic environment in which our quantum system is sitting. And I'm going to show you examples of how V is used. And then here's the wave function again. So to get a solution that tells us what the wave function is, we need to know the environment. And then we do some mathematical operations on this side of the equation and some on that side. And when we find a solution, that solution is the wave function for that system. So we use the Schrodinger equation and a description of the environment to get the wave function. And as I said when we started, the wave function tells you everything. Now we do have a little excitement here, and that's this I, which is the square root of -1. You may have encountered this in your high school or college math. This makes this equation sort of unique among the physics equations that preceded it. This is not found in any other physics equation that preceded quantum mechanics. That is, we have an imaginary number sitting right in the middle of our equation. But it turns out we now know what to do about that. Now, this is an equation that shows us how the wave function changes with time. There's a simpler form. Here it is. If we are only looking at the wave function and how it changes with space, that is position defined by x. We're going to move on. There's more description there that you can read that will fill in the details. But let's talk about the properties of wave functions. Here's the definition. I'm going to move this as a result of this lecture. I'll move this definition of how you pronounce psi and so forth. I'll move this earlier in this chapter so it's logically sequenced properly. The key thing to know about wave functions is they have to comply with certain mathematical and physical restrictions. For example, the wave function cannot do this. This is a problematic thing when you're doing mathematics. So we never expect this kind of a kink in the wave function. We also don't expect this, where the position or time property of the wave function makes a jump like this. Then you wouldn't be able to tell, for example, if this is time, you wouldn't be able to tell, is the value here or is the value down here? So that's not allowed. And you can't have a gap. It has to be smooth and continuous. And it certainly can't do this, where it has two different values at the same time. Those are all disallowed. So when solutions for wave functions are derived, they have to be checked to make sure that none of these kinds of odd behaviors exist. Now, the wave function has other restrictions as well. It has to be zero, infinitely far away from where we're doing the calculation. And if we do the calculation of the probability that involves squaring the wave function, if we look at the wave function over all of space, the sum, the total area under this curve for the wave function has to equal 1. Because we're dealing with probabilities, and as you know, in any kind of, if you're rolling dice or flipping cards or whatever, there's going to be some outcome. So the probability of all the outcomes combined has to equal 1. And the same applies to the wave function. Now you can look at this as an animation if you like to. If we take a regular oscillating function, a pendulum, for example, and look at it in the physical world that we inherit, an object that's oscillating, in this case, a spring and a ball, the ball just oscillates back and forth. Nothing complicated about that. If we look at the quantum mechanical version, because of that square root of -1 that exists in the equation, in Schrodinger's equation, we get two kinds of answers. We get what's called the real part and the imaginary part. And these interact. This is a depiction of the evolution of a quantum mechanical pendulum. And you see all sorts of interesting wiggles and squiggles occur because we're dealing with both real and imaginary mathematical entities. As I say, you can click on this and you'll see an animation of that. And there's more discussion here of the square root of -1 appearing in Schrodinger's equation. If we put this all together and apply it to a real situation, such as where are the electrons in an atom when the atom has different levels of energy, we get these kinds of beautiful results, three-dimensional distribution of the probability of where we would find an electron, for example, in a hydrogen atom. This result depends on the energy in the atom and the electron that's orbiting the proton. Oh, I see a little thing I have to mark here. There's a typo. I think, check that. Different energy levels and different angular momentum situations produce these different interesting shapes for where we might find the electron if we had a way to look without disturbing that atom. And this comes right from the Schrodinger equation. I'll show you more examples of how this is done. Here's another view of if you took a slice through the center of the hydrogen atom and changed the properties of the atom by energizing it with an electric spark, for example, you would find different patterns depending on the energy you give to the atom. Where is it likely that I will find the electron if I had a way to do this? The interesting thing is there are places like right in the middle of this. So you see the circle is my cursor now. Right in the middle of this, there are places where we would never find the electron. If we put it into this state, we never find it right in there, wherever it's black here in these drawings. Even in this simple one, this black ring that you see right there, that's a place you never find the electron. All this comes from using the Schrodinger equation and applying it so that you see these structures. Let me mark something else here. Okay. So let's just take a breather here and ask, are there questions? Yeah, there's a question I'm not going to answer right now, so we'll get to that. Now let me close that. So I mentioned Max Born. Here he is. He was the first, not the first, but he was the clearest voice that the square of the wave function is the probability of the outcome of an experiment, a quantum experiment. Others had considered this, but cast the idea aside. But Max Born, in a footnote in one of his papers, proposed the square of the wave function, such as I'm showing here, is an important physical property. And the context in which he came to this conclusion convinced people that this should be the approach. It took a while, but eventually people began to see that this is a physical property that cannot be ignored. This is his granddaughter, Olivia Newton-John. You might have heard of her. One of the clues that Born presented for convincing the community that the square of the wave function is an important physical property in a quantum system comes from the well-known properties of electric fields that I don't want to do something. Electric fields, such as described by Maxwell in the 1850s, 1860s, that the square of the electric field is a physical property that is related to how much power an electric field has. And for example, if you have a light source, the amount of power that light source is conveying is described by the square of the electric field. So there was already a knowledge in the community that this is the way nature behaves. And this square of the wave function was eventually accepted as an important advance as provided by Max Born. Schrodinger wrote Oh, and I should say, we get our first serious contact with Heisenberg, the author of the uncertainty principle, and Schrodinger's reaction to Born proposing that the square of the wave function is an important factor in quantum systems. And here's Schrodinger writing in a letter. Remember, almost all the communication that occurred in the development of quantum mechanics occurred in technical papers in journals, but a lot was conveyed in letters that the scientists wrote to each other. The bottom line of what we get out of Born's interpretation of the wave function, I should highlight that, this whole thing, interpretation of the wave function is that causality that we're so used to in our interaction with the natural world does not occur in the same way in the quantum world, because Born says the wave function squared tells us the probability of the outcome of an experiment or the behavior of nature, because remember, nature is constantly doing quantum mechanics. The light from the sun is the result of a quantum mechanical process, not an experiment. So most of what we see in the world around us, virtually the only source of knowledge about the quantum world, is virtually everything we see is the result of atoms and subatomic particles interacting under the laws of nature. The experimenters in the lab see additional information because they've created artificial environments where they can do experiments. But all of us interact with quantum systems. Indeed, we are quantum systems. All of us are made of atoms that are presumably behaving just like Schrodinger described, because as far as we know, his equation is absolutely correct. But different outcomes occur in the experimental realm where you can control the quantum system very delicately. And because a single quantum system can behave differently, for example, those atoms that appeared in the video I showed you, each electron going through that double slit experiment is a quantum system, and they all land in different places. So the idea of causality is under attack when we're in the quantum system or the quantum world. We can't, if you hit a baseball repeatedly the same every time, the ball is going to land in the same place every time. We don't get that from quantum mechanics. The equivalent of a baseball bat hitting a ball in a quantum environment, you get the balls landing all over the place. So we have to give up our traditional intuitive expectation of causality in physical systems, because we're dealing with a wave function that evolves with time, according to Schrodinger. And then Max Born tells us that if we use that wave function to predict outcomes of experiments, we get different results every time. Now, there's a little section here that explains that when we got to 1926, 1927, there was a changing of the guard in the following sense. All the prior progress in quantum mechanics, Niels Bohr, Einstein, and dozens of others who made contributions between 1900 and around 1925, those people were getting near the end of their careers because they were all seasoned scientists in 1900 when quantum mechanics first emerged. And then another 25 years went by, and so most of them were entering their 60s and 70s. These new advances, such as from Schrodinger, Born, here's the list, all these people were youngsters You see here Pascal Jordan, 22, Heisenberg, 23. Paul Dirac, who we will hear lots about, was only 22 when Schrodinger's equation emerged in 1926. So there's a discussion here about a new generation of scientists coming into the spotlight. And a few of the older ones, including Einstein, continued to make contributions, but the real inventions, the innovations were coming from a whole generation of young people. In fact, I should point out that Paul Dirac was the first physicist to earn a PhD dealing with the topic of quantum mechanics. Everybody who preceded him had been trained in classical physics. Now we're going to take another quick look at wave-particle duality. And I want to just remind you of the history of this. That if we consider the physical properties of light, hundreds of years earlier, Newton had described light as being particles. He called corpuscles. That got overturned when Thomas Young did this double slit experiment using light. And then Einstein in the early 1900s had shown that particles like electrons can behave like waves. This evolution of reconsideration of wave and particle interchange really became a central issue in how quantum mechanics continued to evolve. A key player was de Broglie, who was the first to really seriously consider how particles and waves can complement one another. And in the modern context, we have experiments such as this one. We're not going to go into detail here by Wheeler. We will talk about this quite a bit, where we have experiments now where we can have one experiment, this setup of mirrors and so forth. In this experiment, we can put a light source into this experiment. And depending on how we change the experiment while the light is moving through the experiment, it will behave like a particle or a wave. This was a concept from a famous physicist, John Wheeler. He had this thought experiment in the 1960s. And by the 1980s, people were building experiments of this kind where, again, you can shoot light into this array of mirrors. And depending on whether you throw a switch while the light is in the experiment, the outcome will indicate that what you injected is a particle or a wave. So I highlighted this one because we will see this many more times. By the way, understanding how to manipulate electrons allowed the development of the electron microscope. If you use a conventional microscope, optical microscope, and look at this biological entity of radiolarian, this is about the best you can do. With an electron microscope, you see this. And this happens because electrons are used in a wave-like way, and we get this extraordinary detail. Now, let's go back to something I brought up 40 minutes ago, and that is, how do we get the wave function that I've talked about so much today? The answer is we have to describe the environment in which the quantum system exists. And here's the first one. This is the first one that physics students do. We're imagining that in this space, this physical space, we have a quantum particle. It could be a photon, electron, neutron, doesn't matter. And it's confined by what we say are infinite this is an infinite well. That is, it takes infinite energy for the particle to get out of this well. We use this with Schrodinger's equation to calculate the behavior of a particle trapped in this space. And the answer is very simple. We get quantized energy levels. Remember, I've talked in the past about what it means to say a system is quantum. It has to do with how we describe it, how it is described in the mathematics. And in quantum systems, the allowed values of things like spin or energy or momentum are all dictated by integers. There can't be a value between 1 and 2. It's either 1 or 2. And we see this explicitly right here for this infinite well. So if we put an electron in at the infinite well, solve Schrodinger's equation, which gives us the wave function, but also gives us the energy. And notice here we have Planck's constant. We have an 8. We have the mass of the particle here, m. And we have the spacing a between these 2 points. I have to fix up a little thing there. Sorry. Yeah, that's what I want. A is the space between the walls. But notice that integer value right there, n. That tells us that energy level that the particle trapped here can have goes as the square of the numbers 1, 2, 3. This is quantum at its most obvious. The energy levels depend on the square of integers. An energy level for a particle in this space cannot have a value of 1.3 or 2.4 or any other. It has to be integers that go right there. This comes directly from solving the Schrodinger equation using, remember I had mentioned in the Schrodinger equation, there's a V. That's this V. Let's look at some other examples. Oh, by the way, if you build a two-dimensional box, an infinite two-dimensional box, and put a particle in it, these bumps tell you the probability of where you might find the particle. In this case, this is the wave function for an infinitely deep two-dimensional well in which you put a quantum particle. See, there's psi, the wave function. How about if we do a different version of this where we don't have an infinitely deep well? It's a well, but the energy required to get the particle out of the well is not infinite. Here we see wave functions, and these little things here are the wave functions that are allowed. But notice they penetrate into the wall right there, there, and there. So there's a contrast between an infinitely deep quantum well, the wave functions that we get from the Schrodinger equation look like this and do not penetrate. But if the well is not infinitely deep, then we get these penetrations. This is really important and has turned into a valuable knowledge for building semiconductor circuits that use what are called tunneling diodes. And we also build microscopes using tunneling technology where the wave function is not zero outside of this space. In a classical sense, if you drop a ball down a well, there's zero chance it's going to penetrate the wall. We also have some other examples where if you put barriers, these pink barriers inside the space and drop a quantum particle in there, this is what the wave function looks like. If you square this, that gives you an indication of where you're most likely to find the particle. In this case, if you square it, the peak is here. You're most likely to find it in this space right in here. You can also do a harmonic oscillator. This is I'm going to probably replace this piece of artwork But it also has this property that the energy of a quantum mechanical oscillator, just like a pendulum, I use this example that it's like a skateboarder in a skate park. If you've been to a skate park with your grandkids, you know that they build these bowls that you can drop into and skate around and so forth. If you put a quantum particle in one of those bowls, that, in fact, I'm going to highlight that. Sorry, I'm working while I'm talking to you, but I got to make this more readable. If we want to put a bowl, a quantum particle into a bowl, we get this kind of energy level. And let's look at this. There's Planck's constant again. Omega represents the frequency of the particle going back and forth in the bowl. And there's the integer that makes this quantum, where n can only take on integer values. The unique thing about this is, at the lowest energy state, there is still energy in a quantum oscillator. You can't make the particle stop moving. It's always going to be in motion in the quantum well. Now let's turn these sort of artificial experiments into descriptions of real things, namely hydrogen and helium. If we use the Schrodinger equation and use the electrical force that exists between the nucleus and the electron, we get the following probability for where we're going to find the electron. In the case of hydrogen, this red curve is the wave function. So we're most likely, we don't find it at the this is where the nucleus is, and then we're going outward. There's a place that depends on the energy level of the electron where it's most likely to find the electron, and then way out, there's very little chance of finding it there. If we could do the experiment, we wouldn't always find it in the same place. This is, remember, we square this to get the probability. In helium, the electrical forces are more intense, and the peak location of the innermost electron, or the electron cloud, is closer to the nucleus than it is in the case of hydrogen. So we can put this to work. Oh, by the way, this is the wave function. These are the probabilities. Now, I've talked about tunneling a little bit. And very early in the history of quantum mechanics, George Gamow, who eventually became a professor at the University in Boulder, he found or did a calculation of tunneling by nuclear particles that suggested he was explaining radioactivity. And this has been confirmed in experiments since then. The idea is that nuclear particles are bound together, but occasionally one of them will be in this situation, an event, one of the nuclear particles will overcome the forces that it endures in the nucleus and tunnel out and find itself leaving the nucleus. So that this is another practical application of tunneling in the nuclear context as opposed to the atomic context. So you can click on this. This is an interesting website. This is from University of St. Andrews, I think. And they have animated experiments where they say, okay, you have, in this case, an isotope of lead, I think. It's a little hard to read. No, it's from polonium that was named for Madame Curie, radioactive polonium, because she was from Poland. Polonium decaying into an isotope of lead. And you can see that graphically. If you click on this, it throws you into a website that has more than just this animation. There's lots and lots of animations of nuclear processes, but one of them is this tunneling process in the nucleus that is explained by the Schrodinger equation. And we have a practical application, namely the scanning tunneling microscope. And these things, here's, by the way, another depiction of tunneling where we have an energy barrier. And here, the energy barrier is greater than the energy of the particle. Nonetheless, the particle can find itself penetrating and leaving. This has resulted in design of a electronic device that has a tungsten tip that you can roll over a item. This is a carbon nanotube where here's the dimensions of this. The picture that you see there has these dimensions. A length of 7 billionths of a meter and a diameter of 1.4 nanometers. And those little dots are individual atoms that are detected by having this tungsten tip interact with the material, and tunneling occurs across this gap. And you can actually form an image of atomic structures. The wave function also spreads with time according to the Schrodinger equation. So if you have this wave function for a small mass, let's say an electron, over time it gets wider and wider. And a larger mass also spreads, but does less so. It spreads, but less dramatically. Oh, yes. In the footnote for this, footnote 63, you can see an animation of the spreading of a wave function. So this is the time-dependent Schrodinger wave function in one dimension, in this case, X. And my cousin's cartoon is, I don't know. You see if you can figure out his droll humor. We also, out of that era, the mid-20s to 1930, we also get the uncertainty principle. And I've talked about this before, where there's an analogy between how the wave function of a quantum system behaves and how optical light behaves. Namely this: if you shine light on a perfect lens, you cannot get it to focus to an infinitesimally small point. If you look at focused light in essentially perfect optical systems, such as the telescopes that astronomers try to build, you don't get focusing of starlight to a pinpoint. You get a structure like this surrounded by echoes. I can see there's a ring here, and then there's a faint evidence of a ring there. It's just the way nature, the wave nature of light resists focusing to an infinitesimal point. The same thing happens in the waves of quantum mechanics. And that's the foundation of this famous equation here. That's Heisenberg's uncertainty principle, explained simply that you can measure the position of a quantum object, but if you make it too precise, you undo your ability to measure its momentum. And the same thing applies to energy. If you insist on measuring the energy of a system very precisely, it takes a long time to do it. This is very important, because this also implies that if you look at a quantum system for a very short period of time, a large array of energies are allowed. And this is something we'll discuss again. It dictates that nature will produce artificial virtual particles that come into and disappear all the time, that a vacuum is full of a churning foam of atomic, subatomic particles and light. And if you look at it real quickly, all energy levels are allowed. If you study it for a while, then the energy levels must be small, because it has to accommodate this equation. So the Heisenberg uncertainty principle really comes from the discovery by Schrodinger that quantum systems accommodate a wave function. And as soon as you say waves, then you have to admit it's going to behave something like this, that you can't squeeze it in one dimension too much or it bulges in another dimension. Here's another way to look at it. If I say I'm going to do a position and momentum measurement of a quantum particle, and I'd like to have the position measurement fairly high precision, the measurement of momentum bulges this way. Another way to say it is the area of this ellipse has to be bigger than some constant. If I'm willing to give up on my measurement of position and allow it to have a range of error, then I can do a better job at measuring the momentum. So this is a discussion of it. Oh, let's do one thing and then we'll take a break. So if I have this depiction of the wave function fairly well confined, it will have an associated momentum. But if I then take that momentum and confine it to be more precise, that forces the position to spread out. So I have more fuzziness in position when I have a high quality measurement in momentum. All right, this looks, oh, and they're different. Indulge me for one more minute. There are different kinds of uncertainties. So here's energy and time, momentum and position for both the double slit, the particle in the box, microscope, a gamma ray microscope. Here's that quantum mechanical oscillator we talked about, where the quantum particle is trapped in a well. It still has to obey the uncertainty principle because the descriptive property of all quantum systems is the wave function, and that word wave is key. If it's described by a wave, then there will be a limit to the quality of measurements you can make. Now, let's stop at this point. We're about halfway through, and we'll take a 5-minute break. And when we come back, we will resume the rest of this chapter in the book. So I'll see you at 2:07. Well, it's 2:07 and we're back. Now, I've made a lot of claims about the success of quantum mechanics, and we all own the evidence that quantum mechanics works. Cell phones, television, flat screen TVs, and so forth. But let's take a look at some more technical demonstrations of the ability of the Schrodinger equation and its partner, the wave function, to actually describe nature. And here are a few examples, a few of the thousands and thousands of examples that exist. Whoops, here's one. It's called Bose-Einstein condensation. An Indian physicist wrote a letter to Einstein in 1924, I think, where Bose demonstrated to Einstein that he had a deep insight into what was going on in the quantum world, and they collaborated. And in their collaboration, Einstein predicted that individual quantum particles, if brought together under the right conditions and at very low temperature, that a group of particles would behave as a single quantum entity with a single wave function, which is here. And indeed, this was finally demonstrated in 1995 at the University of Colorado and working with MIT. And they produced something called Bose-Einstein condensation, which ultimately led to a Nobel Prize. This is a unique state of matter in which a group of, in the case that they did, working with sodium or rubidium atoms, produced a cloud of tens of thousands of atoms that coalesce into a single quantum entity. And again, a Nobel Prize. And Schrodinger's equation and work by Einstein and Bose predicted this. It took almost 100 years to demonstrate it, but nonetheless, there it is. We have another example, so-called Casimir effect in the late 1940s. Henrik Casimir, a Dutch scientist, predicted the foam that I mentioned just before the break, that there were virtual particles churning into existence in a vacuum situation. I'm not going to go into the details here, except to say that he had in mind in 1948 how to do an experiment to determine if this churning foam of particles and waves could actually be detected in an experiment. And it took 50 years to demonstrate the Casimir effect. And now we're going to switch to the, hang on. Oh, I know I have to do, excuse me while I fumble around a little bit here. And let me make this fit the width. So there's the concept of Casimir's experiment. 50 years later, we have this actual implementation of the experiment. The line is his theory, and the dots are the measurements from this apparatus. Again, quantum mechanics predicts this strange behavior of that really comes from the Heisenberg uncertainty principle. Remember, before the break, I showed that if you look briefly at a volume of space, the energy levels that can exist in there can be huge. Indeed, they can be physical entities that last for a short period of time. And sure enough, Casimir's prediction turns out to come true. We also have the case, also dating from the 1940s, of predicting the magnetic property of the electron. there was a coincidence of theory and measurement in this case. It didn't take 50 years as it did in the Casimir case. That predictions were made by two Americans, Schwinger and Feynman, and a Japanese, Tominaga, how to calculate the electron magnetic moment, the magnetic property of the electron due to its, what we call its spin. And in the early 50s, not more than 5 years after their prediction, the technology existed to actually measure this value very, very precisely using microwave techniques that matured during World War II. Here's a comparison of the two results. The theory said that the value should be something like this, with a little fuzz on it. And the measurement, you will see, matches the theory until we get to that digit right there. We get to the 10th digit before there's a deviation between the theory and the measurement. This comes from a derivative right from the quantum mechanics of the 1920s, extended by those three individuals. And the match is extraordinary. This is the best prediction in the history of science. This value right there. Because look how it matches the measurement. Now we're going to do our first kind of detailed look at, hang on, I'm going to do something. We want to take our first more or less detailed look at entanglement. I already talked for a few seconds early in this presentation about entanglement and how it is created and its really extraordinary properties. The fact that entanglement exists was predicted by Schrodinger in 1935, under conditions that we will deal with next week. An extraordinary prediction. What he said was that if particles interact in the right way, as long as they don't interact with the world around them, they are bound together no matter how far apart they are or how long they are in this bizarre marriage. And it took from 1935 until Madame Wu, 1950, actually observed entanglement. She may not, you'll see the details if you read the book, you'll see the details. She and her student did an experiment that demonstrated entanglement, but they were looking for something else at the time and did not realize what was going on. But she definitely gets credit for being the first to produce entangled particles. So this cartoon is supposed to help you understand this. If we produce here two entangled particles, in this case photons, they're created together in the decay of an atom that, when it goes from a high energy state to a lower energy state, produces entangled particles, or entangled photons. And one of those particles leaves the place where they're created and heads off toward Alice, and the other goes the other direction and goes to Bob. And we always use Alice and Bob to populate these experiments that we will be talking about. And Alice and Bob, you can see depicted here, Alice is in Seattle and Bob's in Boston. And here's the way entanglement works. A whole stream of photons go to Alice, and she measures their properties. And Bob gets his own stream of particles, and he measures his properties, the properties of the particles that he gets. And what Alice and Bob each get appear to be random orientations of the polarization of the photons they get. Remember, we worked a little bit with polarized sheets a couple of weeks ago, and I pointed out that the polarization that we see and exploit in our sunglasses also applies to individual photons, can be polarized. They have a certain spin orientation. So Alice gets a list. Depicted here is a list of random orientations. She's in Seattle. Bob has his own list. But when they compare lists, if you look closely at this cartoon, how do I make that? Oh, zoom to. Well, I don't know how to make it bigger right now. Well, maybe I can. No, I don't know how to make it big enough so that you can see it. But when she gets a 1, he gets a 0. And when she gets a 0, he gets a 1. And if you go through this whole list of random orientations that Alice gets and that Bob gets, the results are correlated because the particles were created in the same quantum event that produced 2 entangled particles. People have recently done experiments that we will see in lecture 5, where large numbers of particles are created in a quantum event. 10s or 20s of atomic particles or subatomic particles that are correlated just like this. And this extraordinary property of entanglement can be used to conduct experiments to explore the nature of the quantum world. So entanglement is, oh, there's Madame Wu, by the way. This entanglement feature of quantum mechanics, predicted by Schrodinger in 1935, remains one of the strangest properties in any form of science. It's just not something you would expect, but it comes right out of Schrodinger's equation, and we will be talking about it a great deal more. Now, we're also looking for applications of our current knowledge of quantum mechanics. I keep saying, well, we have lasers and we have electronics and so forth. The first application of the modern version of quantum mechanics that emerged in 1926, 27 is an explanation for the periodic table. And when we get to the end of this, you'll see that Richard Feynman was right when he said theoretical chemistry is physics. So let's take a look at this with quick history. Here's a periodic table from the 1860s from Mendeleev based on chemical reactions, where just working with atomic species that existed at the time, people understood that how you add things together, that sodium and chlorine like to be together and produce salt and so forth. So there was an effort to organize the 70 or so elements known at the time into groups. You see the word group here, and organize it in a way that came from the way chemistry works. But chemistry is all dictated by how electron clouds of atoms interact. If you bring a sodium atom and a chlorine atom together, they start sharing electrons in a specific way and form solids that can be melted, dissolve in fluids and so forth. So we have this early version of the periodic table. What we needed was an organizing rule based on quantum mechanics. And I've shown you this before. This is the genesis of all the elements in the universe from different types of astronomical events, except in the case of humans synthesizing these heavier elements. And the organizing rule, you've seen this before, the organizing rule is the Pauli exclusion principle. And Wolfgang Pauli came up with this by looking at the properties of wave functions the mathematical structures that are allowed in atoms orbiting nuclei. And if you look at the properties of the electron using the Schrodinger equation and the electrical situation that electrons are in when they orbit a nucleus of an atom, Pauli came up with an exclusion principle that said that the energy level of an atom, let's take hydrogen, sorry, let's take helium, the energy levels can be duplicated by multiple electrons only if their spins are opposite. That there's no situation where multiple electrons in the same orbital cloud can have all the same quantum numbers. So you've seen these before, but we're now going to use the professional language, the quantum numbers for energy, orbital spin, or orbital angular momentum, and spin. So energy comes from that integer, angular momentum comes from L, and this quantum number relates to the spin orientation of electrons in a particular shell. So the exclusion principle says you can fill the electron shell of any atom with as many as the electrons you want, as long as you do not violate the rule that there cannot be duplication. That each electron in that shell has to have a unique set of quantum numbers. So other values are excluded, hence the name. This, as soon as that was discovered, it allowed Niels Bohr to start demonstrating how you build the periodic table. But before we do that, let me illustrate how this works. Years ago, 50 years ago, I had friends who were rock and roll promoters, and we would go to concerts, and I was the stage announcer frequently. And you see some of the people that I was on stage with there. And what frequently happened is that the cheap seats would fill. People would buy the cheap seats. The expensive seats in the front rows were not so likely to be fully filled. And occasionally the performer would get the message to me to go out and say to the crowd, if you want to come forward and sit in the front rows, you can, which would no question irritate the people who paid more for a reserved seat in the front row, because now we have this. People left their seats in the back of the auditorium and came and filled the seats near the front. But these were disciplined people. We never had two people in a seat. And by that, I'm comparing this to the exclusion principle. There was a place here in the front row, and eventually somebody would come and sit there, but we never had this. We always had disciplined people, a mature crowd, and they filled each seat. So there was a unique individual in each seat, but we did not have a mosh pit. And that's what Pauli was explaining. That's how atoms work. You can't have all the atoms crowding into the inter shells. They're forced to take on a unique quantum number for energy, angular momentum, or spin orientation. So when this idea of the exclusion principle was announced, Bohr, I think, was the first to say, I know how to build and that's German, Aufbau is the German for assembly. Bohr said, I know how to build a periodic table. If I have one proton and one electron, I can put that electron into the innermost shell of an atom, and it will be hydrogen. And that is not the number one. That's an arrow, point that in hydrogen, the one electron that's present can either be up or down, but it's only one. And if I insist on adding another proton to this atom, now I have two charges in the nucleus, I can add one more electron in the inner shell, one oriented up and one oriented down, and we have helium. And if I continue this to produce lithium, now I've filled the inner shell. So an additional electron cannot get into that shell. It goes into the next higher energy level. If you took chemistry, you begin to see what we're getting here. Here's the electron configuration for lithium, which has 3 protons and 3 electrons, and beryllium has 4 of each. And the only difference between lithium and beryllium is we've added another electron to the 2s shell, but they have to have opposite orientations of the spin of the electrons. And here's boron, adds a 5th, and we're on our way to building much heavier atoms like neon, sodium. So here's sodium. It has 1 electron in S, 2 in there, and so forth. So this is the concept that Bohr used to build the periodic table of elements. And here it is depicted in all its gory detail. And you notice they use this shortcut, that lithium is really helium with an additional electron. Beryllium is helium with 2 additional electrons. Boron is still helium, and then eventually you're producing neon, and from that point on, it's neon with additional electrons, and so forth. I don't know what this is. Huh? Now, a pertinent question is, what are the shapes of those clouds of electrons? I've already shown you the shapes for hydrogen and helium. Here's a more elaborate description of the probability of finding electrons in 3 example atoms, helium, neon, and argon. Here's the distance, and you see we're talking about picometers. That's a millionth of a meter between the nucleus here at 0 and where you might find the electron in, I got to decode this here, purple, green, red must be neon. No, where is red? In any case, helium is green, neon, argon. Okay, this curve is the result of the Schrodinger equation calculating the likelihood of finding the electron, an electron, in the electronic structure of argon. And the lowest energy level electron is pretty close to the nucleus, which is right next to it. The next higher energy level is farther away, maybe 10 picometers. And the next higher shell is here, peaked at around 70 picometers. So this all comes from analyzing the Schrodinger equation in the context of atomic structure, where you have a nucleus that has charge and electrons with negative charge. And in fact, here's the periodic table reconstructed to show the size. These little circles show the relative size of the clouds of electrons that are around the nucleus. So there's hydrogen and helium. And you see that helium, which has 2 protons, that dot is very tiny because the 2 electrons draw the that little dot represents the size of the electron cloud. And the two electrons in helium get drawn close to the nucleus because the electric force between the protons in the nucleus and the charge of the electrons in the electron cloud is stronger for helium than it is for hydrogen, which has only one proton and one electron. And you see cesium. Is that cesium? I guess. I'm not sure. I'm not a chemist, so you'll have to excuse me. But you see the cloud is big. Now, of course, this is all relative because we're measuring everything here in picometers. And it all comes from this. Here's the Schrodinger equation, and I'll just reiterate. There's the Planck constant, the mass of the electron. The wave function here is shown as a U. I'm going to fix that in the next version of this chapter so that it has a psi there instead of a U. And this V dictates everything because it is the energy level that is defined for a particular one of these atoms. It's different for every atom because every atom has a different number of protons and electrons. So once you have that, just like those examples I gave of an electron in a well dictating the energetic environment of a quantum particle, V here dictates the energetic environment of electrons in atoms. Now, this is a one-dimensional version of the Schrodinger equation. It only has X, but atoms are three-dimensional. So I'm just going to show this to you. Again, we're not doing math. Here's the three-dimensional version of the Schrodinger equation. Done the way we do, see this right here? Done the way we do navigation on Earth. We use two angles, latitude and longitude, and the radius of our planet to depict the location of objects. Like if you want to know where an airplane is, it takes three numbers: the altitude for an airplane added to the radius of Earth, plus a latitude and a longitude, and the same thing applies in atoms. And if you go through this, you'll say, of course, these are mathematical symbols. But we have Planck's constant, mass, electric charge, and a few other physical constants. You have to solve this equation to do the electron clouds. Much more complicated, but we have computers. And this is a doable problem, and it's been done for a lot of different cases. Here's an example. These spheres, now we have a cutaway here so you can see the detail, but these are the probabilities of where electrons will be in a particular atom. And you see there are these nodes, regions where the electron cannot exist. It's like a turducken. You're familiar with turducken, I'm sure. We have a chicken, a duck, a turkey, with space between them. Again, we have the energy levels dictated by integers. This is a quantum system, after all. And if we plot this as a distance from the proton or the nucleus, we get these peaks where we are most likely to find electrons orbiting in these particular atoms. Now we can actually take pictures of this. Here's an experiment described in detail here, where laser energy is used to change the energy levels in the electron cloud of atoms under study. And then electric fields are used, and you essentially get a shadow showing you where the electrons are. And this is a result of theory. But if you do an experiment like this, you actually can see how the theory agrees. Now, I want to make sure we cover how quantum mechanics has changed since its modern version appeared in the late 1920s. That was not the end. I've already mentioned Paul Dirac. Let me do something here. So here's Paul Dirac. He was a pioneer in the next step in applying quantum mechanics to a broader range of problems. And his progress was in the field of what is called quantum electrodynamics. That is, how do quantum particles interact with electric fields? A simple way to describe this is, how do electrons interact with light? And Dirac was a pioneer in this. Remember, he only got his PhD at the age of 22, and right at the beginning of the quantum age, and he was a master mathematician. Out of his work, he predicted the existence of an antiparticle of the electron. And that's nowadays, I think he coined the name positron. These particles were theoretical in every way after he predicted them for only about 3 or 4 years before people studying cosmic rays actually found a particle with the mass of the electron that could get that out of the tracks they found in bubble chambers. They could see the track of a particle coming from outer space going through their bubble chamber, leaving behind a vapor trail. And the curvature of the vapor trail told them the mass of the particle and its charge. And they discovered occasionally that a particle with the mass of the electron would pass through the cloud chamber with a positive charge as opposed to the electron's negative charge. This opened the door to the whole field of antiparticles. And we now know that virtually every particle has an antiparticle. A few oddballs, like the photon, have an antiparticle that's the same as the particle itself. But virtually every quantum particle has an antiparticle. This all comes from Dirac producing an equation that predicted an electron with a positive charge. So I just make a philosophical point here. When people predict particles, when theorists predict particles, and the particle is eventually found, we have to respect the knowledge that we have about the physical world. We don't have complete knowledge, we know that. But what we have is so close to reality that we can predict particles or other kinds of behavior. And then if we find it in nature, we have to be on the right track. And yet we're using mathematics that comes from the logical developments of the human mind. Why is it that the mathematics that we use for any branch of science actually works when it is applied to the physical world? This is a philosophical topic worth chewing on, and there's no clear answer why that should be the case. And yet we know it works. Here we have one case of Dirac predicting an anti-electron, now called the positron, but it's not the only case. And I'm trying to remember, oh yes. So I just want you to keep in mind this idea, extraordinary development, that a mathematical toolbox is able to predict how nature is going to function, but that can't be what nature is doing. Nature is not using Dirac's equation. Nature has its own way of working. We don't understand yet what fundamental behavior in nature is causing it to give us quantum mechanics and other features of the physical world. And yet mathematics is a very capable, extraordinarily capable tool for understanding these systems. We now know, by the way, that electrons are part of a family of 3 electrons of successively larger objects. The electron is the lightest. It has a cousin, the muon, and has a much larger cousin called the tau. And we'll talk about those, I think, actually in this lecture. So quantum electrodynamics takes advantage of what we know about the interaction of charged particles and light, and has been successful. The next generation of researchers after Dirac were the 3 I already mentioned, who predicted the magnetic properties of the electron and won a Nobel Prize for actually getting the number right, an extraordinary achievement. In the case of virtual particles, the theorist has to deal with the following challenge. We have here in red a negatively charged electron. It is surrounded by a vacuum, but that vacuum immediately is filled with virtual particles. Most of them are charged particles. So the presence of a negative electron here will attract, I don't know if you can see, this little ellipse has a plus right there. Any charged particle that pops out of the vacuum, even for the briefest instant, is attracted to this electron, because the negative charge here and the positive charge here are attracted to one another. So this electron is surrounded by a cloud of charged virtual particles. And so from a distance, this structure, which only lasts for a very short time, it appears to be a negative object because the negative tails of these virtual particles are sticking out over here. It looks like, from a distance, it looks like, oh, there's a negatively charged object over there, but it's much less charged than the electron that caused it to form in this way. So the mathematics of how you describe this kind of system gets very complicated very quickly, and all sorts of gymnastics had to occur for researchers to come up with the way to calculate these things. The result is we now know that in Bohr's day, the energy levels of atoms were like this. Dirac showed, no, there's hidden, if you're precise enough, there's hidden energy levels that you can't see unless you do a very exquisitely careful experiment. So there's Bohr and Dirac's development beyond that predicted additional energy levels, which have been found. So again, the mathematics of quantum electrodynamics gives us these predictions, and if we look hard enough, sure enough, we find them. There's a repeat of the agreement in the magnetic properties of electrons. I'd just say one little side note about Schrodinger. He had a very colorful life. He had many mistresses. Most of them lived with Schrodinger and his wife all at the same time. He was a notorious womanizer, but he didn't just think about quantum mechanics. He wrote a very influential book in 1944 called What is Life? This is essentially 10 years prior to the discovery of the DNA structure that dictates our genetics. And his little book called What is Life actually muses about what is it that is in the cell of biological systems that allows those cells to reproduce but specialize. And what he didn't realize, he was talking about the structure of DNA. And in fact, Schrodinger was given a lot of credit by the discoverers of DNA, including Francis Crick, for guiding Crick's thinking about what is it's going on in cells that allows for reproduction. Another bizarre thing about Schrodinger is that there's a relatively young researcher, he's probably in his 50s now, who discovered that Schrodinger was a grandfather, in spite of the fact that Terry Rudolph also became a quantum physicist in his own right. So there's a little history there. You can see here's a letter from Crick to Schrodinger, thanking Schrodinger for guiding Watson and Crick to the structure of DNA. Here's Feynman, Schwinger, Tominaga, the three that developed the theory of the magnetic properties of the electron. And the only person who understood all three of their developments was Freeman Dyson. I've seen depictions of meetings that, for example, Feynman had with Julian Schwinger, where one said to the other, "Tell me how you did the calculation." And the other guy talked for a while, and the guy who asked the question said, "I don't understand anything you're saying." And of course, here's Tominaga, who was working in Japanese, and these two are Americans. Dyson studied all three theories. And here's, Google is telling me this is a picture of an old person standing in front of a blackboard. Thank you for that. Freeman Dyson studied the theory of all three of those individuals and managed to reconcile how they all got the same answer in spite of doing it completely differently. And you'll see in here, in this little panel here, a description of the time I met Freeman Dyson briefly. Now there's a further development from quantum electrodynamics called quantum field theory. And quantum field theory is an extension of the quantum mechanics that we all know and love, and has been very successful in predicting the family of subatomic particles we call the Standard Model. There's a discussion here of the evolution of this. Here's the Standard Model of particle physics. I have another drawing I'm going to show you in a minute. That the electron, its cousin muon and its cousin tau, which didn't get in here, are all in a group called the leptons. These are light particles and they have spin 1/2. Baryons, which are force conveying particles, so a proton, the neutron, so forth, also spin 1/2. Then there's a group of particles that interact with both of these groups, the ones in green. Those have spin 1, and they are subatomic particles. That is, if you smash protons together, you get W's and Z's. And there's another group, the pions, no spin. The photon has a spin of 1. And there's a particle we're still looking for that conveys the gravitational force. It has a spin of 2. In theory, has a spin of 2. It has not been seen. So here's a depiction of foam, and I think the reference provides you with an animation of that foam. So let me get to, we have a few more minutes. Yes, I do want to talk a little bit about another extraordinary feature of quantum mechanics. Quantum mechanics was built to explain the behavior of atoms and the behavior of black bodies. Remember, the invention of the quantum by Max Planck in 1900 was all about explaining the black body curve that had been observed in industrial settings, but had not been explained until Planck made the desperate move of saying, I wonder if the light coming from an oven is quantized. And when he did that, he suddenly had an answer that matched the measurements. So we have a small number of topics, atomic physics, thermal physics, where quantum mechanics explains virtually everything. The periodic table, light emission from atoms, electron clouds, chemistry, all that comes from atomic physics and thermal physics. But the same technology, the same mathematics, the Schrodinger equation, and the concepts of the exclusion principle and the uncertainty principle, all those also work for nuclear physics. Now you might say, well, every atom has a nucleus, so how different is a nucleus from the atom itself? The size scale difference is enormous. It's like the comparison of the size of the moon of Earth to the size of the solar system. It's actually bigger than that. The nucleus of an atom is exceedingly tiny and has forces and particles churning around down there that are nowhere otherwise related to the size of atoms. And yet, the technology of quantum mechanics applies very successfully to nuclear physics. So I have a little history here depicted right here. The extraordinary success in quantum mechanics applied to nuclear physics, with the biggest leap forward occurring in the 1930s. And of course, we're all familiar with the unfortunate side effect of understanding the nucleus because of its implications for building nuclear weapons. But when we look at the scientific development, the 1930s was a revolution in our understanding of physical matter. The biggest changes occurred in 1932. At that point, quantum mechanics was coming into focus. A lot of the ideas had been around for years, and people, the leaders in quantum mechanics, began looking for other topics to attack, and one of those was Heisenberg, who made enormous progress in describing how the nucleus of an atom is held together. Remember that the nucleus, which is a tiny, tiny thing, has packed into it protons, charged particles bumping into each other, and they have the same charge. So if we use the analogy we have for magnets on your refrigerator, these things want to be far apart. Charged particles want to be away from each other, and yet there's something going on at the nuclear scale that holds the nucleus stable. In addition, the neutron has an interesting property. If you have free neutrons, which you can produce in nuclear reactors and lots of other systems, Neutrons are unstable outside the nucleus of an atom. They decay into a proton and some debris particles. So being able to describe the physics at that scale, the subatomic scale, so it was surprising to find that quantum mechanics that was known by the 1930s applied. Lots of brain power had to go into understanding the details. Nonetheless, the discovery of an array of new particles, including this neutrino, a prediction, again, like Dirac's prediction of the positron, the neutrino was predicted to solve a problem related to nuclear decay. And there were, at the time, several different ideas about how to solve the problem. And Fermi and others figured out eventually we have to invoke the existence of a new particle to make things work. And it took many decades before the neutrino was actually found, but it was predicted in 1933. So we're almost out of time, yes, and there's a lot more discussion of 1932. Here's a vapor trail that I mentioned in a cloud chamber that revealed the existence of positrons produced by cosmic rays striking Earth's atmosphere. And so I have a discussion here of the development of nuclear physics. And here's another depiction of the subatomic zoo, the standard model of particle physics that has the electron family, the neutrinos that were predicted in the 1930s. And now we know about a new set of particles, the quarks, that make up protons, neutrons, and other subatomic things. And we find those by going to CERN in Geneva and smashing protons together. So there's more discussion here that you can review. So in summary, for this chapter, we have a modern, mature branch of physics with all the mathematics laid out. The calculations are difficult, but we use computers to do them. And we understand the fundamentals of how the periodic table goes together, how electrons and photons interact in great detail. We have a standard model of particle physics. One could argue that by, say, 1937, 1938, virtually everything we needed to know about the physics of matter was in hand. But we will find out next week that there's drama afoot, because the reason why quantum mechanics is so successful could not be explained. And that will be our topic for lecture 4, which is next week. And with that, we're going to bring this to a close. I thank you for your attention, and I'll see you next week.